All right, good morning. Good morning. Okay, let's try that again. Good morning. Much better. Okay, today we're going to continue. We're actually going to start a new chapter, 13.1. We'll be looking at what are called vector functions. And these things called space curves. A vector function is exactly what you would expect. It's a function that gives you a bunch of vectors, right? So, a more precise definition this is a function whose input or domain is a set of real numbers and whose output or the range is a set of vectors. Okay, you put a number into this function, and out comes a vector. And you put another number in there, out comes another vector. Here's an example. R is a function of t, and it's a vector. The x component is t minus 2 over t plus 2. Y component is sine of t. And the z component is the natural log of 9 minus t squared. Okay, so you see t is the number you put into the function. You decide what t is. And for each t you can put in there, that's allowed to go into the function. You get an x component, a y component, a z component, and that gives you one vector. And the things that you know about functions still apply. For example, the domain of this function, this vector function here, the usual things you look for, you don't want to divide it by 0. You don't want to have a natural log or any log of a negative number, right? So by inspection, we see that domain is t is not equal to negative 2. And also 9 minus t squared must be strictly greater than 0. There's no restriction on sign. We can put any real number into the function sign. So very quickly we can see that this means t squared must be less than 9. So t is strictly between minus 3 and positive 3. This will satisfy that. This will be the domain of that function. This will be the domain of that function. These two things put together is the domain of the entire vector function. And here we take this one and remove this point, t minus 2. In the interval notation, we would write it this way. Right? We can have anything from minus 3 to minus 2, not including either of these numbers. And from minus 2 to 3, again, not including any of these numbers. So you know how to find the domain of each scalar function. When you want to find the domain of a vector function, it's the same thing. You want to make sure each scalar component is defined for this set of real numbers. What about the range? of this vector function here. What do you think? Let me focus that. Let me rewrite the function here. We'll take a look at the range. Look at each component separately. For any number from that set we choose, the value of t, we know this is always between +1 and -1. So that means the y component of this vector will be no bigger than +1 and no smaller than -1. It can only point up this much or down this much. So that's the y component. What about this? What's the natural log of, what's the range of the natural log function? Positive number, is that it? Assuming 9 minus t squared makes sense for the natural log function. What do you think? What does the natural log graph look like? We should know this. What's the x-intercept of the natural log graph? 1, okay? What happens to the left of 1? We need to know this, people. Come on. It does exist. Yes, what do you think? Yeah, it looks kind of like the square root. To this side, yeah, if it resembles the square root, you're absolutely right. What about the other side of 1? Very good. It goes down like that, right? So that's our natural log function. We need to know what basic graphs look like. Actually, you need to know what basic graphs look like. Okay, so this tells us that the natural log function, assuming 9 minus t squared makes sense, can cover any number from minus infinity up to positive infinity. And this means that the z component can go all the way up, all the way down, and wrap itself around. Right? So then this can also be any number, assuming that t plus 2 is never allowed to be 0. So basically, we're going to get a vector that has no restriction on the x and z components, but has a restriction on the y component. Can point in any direction. But the y component can only be between 1 and minus 1. But the story here is the same. Everything you know about scalar function, as far as domain and ranges go, still apply to a vector function. You just got to remember now we're dealing with a vector and not a scalar anymore. So we're dealing with something that can point in certain direction, and of course the length can change depending on what those components turn out to be. So focusing on the three-dimensional vector function here, let's call the x component f, the y component g, and the h for the z component. And let's assume that f, g, and h are continuous. Over some interval. Then if you collect the dots defined by the tip of each vector, then you get what's called a space curve. The collection of all points defined by the tips of the vectors is called a space curve. It's a curve in space, right? It's a three-dimensional in this case. Okay, so for example, if you spot something, maybe a bird, an airplane, and you want to point it out to your friend, you will point at it and say, look, look, look. The motion that your arm traces, looking at the tip of your finger, that traces out what's called a space curve. It's some kind of curve that lives in a three-dimensional or whatever dimensional space defined by the vector. And you have seen this already. You've seen this already. When we were dealing with lines, right? This is a straight line that goes through the point 3, 5, 0, and parallel to the direction 1, minus 2, and 1. So it's a line, but it's a subset of all the possible space curves you can get out of it. And just like dealing with the line, we can rewrite the equation in the parametric form. Which all it does is, if you remember, is listing the x and y and z component of that curve, in this case, a line. Okay, so again, you know you've dealt with space curves already, just a line. And now we're going to generalize that so it's no longer just a line, it could have any kind of shape. But you can write out the parametric equation, the symmetric equation, the things that you could do to a line. Okay, so this one is not a line anymore. And we'll see what this turns out to be. All right, the space curve here, the x component is sine of pi t, the y component is t, and the cosine, and the z component is cosine of pi t. And first of all, what's the domain of this function? All real numbers, right? T, of course, can take on any real number. Sine and cosine also can take on any real number you put in there. The range will have a vector that has no restriction on the y component, but the x and z components are between +1 and -1. So that's the range of the vector function. So let's see what this looks like. There are two ways to sketch this. The first way is we collect a bunch of dots and then connect them. Make a table of points. And you've done this with two-dimensional curves. You choose a bunch of t values, and then you find out your x, y, and z. And then you connect the dots. Right? It's not a very complicated way to do it. It takes a little bit of time, but it gets the job done. All right? So we all know what sine and cosine do. Basically, if you can figure out part of what they do, they just repeat over and over again. And let's choose a few convenient values of t. 0 is a good number. At 0, we have 0, 0, 1. So the first dot we can put down is 0, 0, 1. If t is 1 over 4, then we have sine of pi over 4, and that's square root of 2 over 2, 1 over 4 for y, and then square root of 2 over 2 for z. If t is 1/2, then sine of pi over 2 is 1. This is 1/2. Cosine of pi over 2 is 0, and you get the idea. That's a 0, that's a 1, that's a -1. And once we know the first quadrant of each of these trig functions, we know what they will do for the next few cycles. So that should be all the information we need to get a pretty good sketch. And once you put these dots together, the first one here, for example, 0, 0, 1. X is 0, y is 0, z is 1. So there's 1 right here. That's at t is equal to 0. And as t goes on, y grows with t. At t is 1 over 4, we move to y is equal to 1 over 4 in this new plane here. And here we have the x and z numbers. So the next one might be, I don't know, something like this. And as you continue, what we end up getting, we will get this shape. This shape is called a helix. Each cross-section with respect to y, each y cross-section looks like a circle. So this is a circle that keeps growing in the y direction. It's like a slinky. You take it out of the box, it looks very slim. But as you stretch it out, the wire traces out this very similar shape. It's a helix, looks like a slinky. Can you visualize it? Yeah? Okay. So that's one way to graph it. It's not very sophisticated. It's not difficult to do it. But again, it gets the job done. Another way is to try to find out the relationship between x, y, and z, if there is any, and then use that to come up with a shape. Not always doable, but often you can find some kind of relationship. All right, so here's the curve we have. Ignore y for the moment. We know from basic trig identity we know that x squared, that's a z, sorry, x squared plus z squared is equal to 1, right? For any value of t. Sine square of something plus cosine square of something else is always equal to 1. So this is telling you that the cross-section in the xz plane or trace in the x and z plane is a circle. If I'm looking down at the x and z plane, either from the positive y or negative y direction, I see a bunch of circles. Now the y component is growing with t. And now knowing these two things, we see that we're going to see a bunch of circles in the x and z plane, but this circle will be stretched out and moving along as t goes to infinity. And in the end, you will get exactly the same shape, of course. X and Z plane, we see circles, but this circle is being moved along, if you want to think of it that way. And then that vector will trace out that same helix shape. And it's always very important to indicate the direction. This alone doesn't tell you the complete story. Does it go this way as t gets bigger, or does it go that way? Knowing the space curve, we know it goes to the right, to positive y. So very often, we will want to have some kind of indication of the direction of increasing t. So let's put it down here too. It's the same shape, of course. And now I have a very, very clear indication of what's going on, what this vector is doing. So this vector is, remember, the green curve I have here is the collection of all the points that's defined by the tip of that vector. So you got this thing here swinging as time goes on. Imagine a vector fixed at the origin, tracing out this green curve as time goes on. That vector will get longer as time goes on, of course, but it will always give you this helix shape. And this will actually be the surface of a cylinder. This green curve here. Imagine there's a cylinder growing in the y direction. And then on that surface, that's where this green curve will be. Questions? Speaking of surfaces, let's find out the intersection of this helix with a surface. Find the intersection points, possibly plural, of a space curve defined by this vector function, the same one we just looked at. And the surface y is equal to x squared plus z squared. Okay, the space curve we just looked at, we know this is a helix. What shape is this? Y is equal to x squared plus z squared. Use traces. Paraboloid, good. Paraboloid. It's not a cylinder because all three of these variables show up. That means the cross-section is going to depend on all three dimensions. This can't be a cylinder. So we're dealing with a paraboloid. And once again, use traces. Imagine y is some fixed number. This tells you that for each slice in the y direction, we're looking at a circle. A circle is going to grow as y grows. Now in the y and x plane here, z is some number. And if it helps, cover up z here. This tells you what y and x will do. In the y and x plane, we're seeing parabolas. And the value of z will change the vertex of that parabola. Same thing here. Covering up x here, we see y and z. We got a bunch of parabolas again. So we got parabolas in 2 dimensions and a circle in one of them. We're dealing with a paraboloid. And y is not square, so this is growing in the y direction, kind of like that. Okay, so that's the surface, a paraboloid. Now inside and outside and on the surface, actually, we have this space curve that we saw in the last example. So it's doing its thing like that. And by inspection, just visual inspection, we expect to see at least one point of intersection, right? At the y equal to 0 plane, the space curve has a radius of 1, and the paraboloid has radius of 0. And as y goes on, the situation gets reversed. At some point, they must have an intersection. And to find this, to solve this problem, it's very much, actually it's exactly the same as the problem we've solved earlier. A couple lessons back, we looked for the intersection of a plane and a line, right? You remember that? Same thing here. Remember, intersection means that there's one point that's on the space curve and the surface. Right? At one point has to be on both of these shapes at the same time. So that means at that unknown t, x is equal to sine of pi t, y is equal to t, and z is cosine of pi t. So that one point will also be on the paraboloid. So what do? We just sub that into y is equal to x squared plus z squared. Right? At one unknown t, or maybe possibly multiple unknown t, the point on the space curve has to be on the surface. So if I just take the space curve xyz into the surface, that should allow me to find t. And once I know t, I can find a point. Okay, so let's see. We get t, that's y, right? X squared plus z squared, sorry. And we know sine squared of something plus cosine squared of that very same something is always equal to 1. And this tells you right away that t is equal to 1. And that's the unknown t. That's going to give us a point that's on the space curve and on the surface. The intersection occurs at t is equal to 1. And the location is at x is equal to sine of pi which is 0, y is equal to 1, and z is equal to cosine of pi, which is minus 1. We're looking at 0, 1, minus 1. 0 for x, negative 1 y, and negative 1, positive 1 y, and negative 1 z, somewhere down here. That's the intersection. And there's only one. Once the helix goes into there, as the paraboloid grows, the rest of that helix is going to be entirely inside the paraboloid. This is the only intersection we can find. Make sense? Questions? Right? It's exactly like finding the intersection of a line and a plane, right? Exactly the same. All right, so now let's talk about a slightly more complicated situation. Along the same topic here, if you have two space curves, imagine that each one has an object traveling on it. And these two space curves may intersect, right? So we're talking about two kinds of things here. The intersection of two curves. That's pretty easy to see. But each one has an object traveling on it as time goes on. If these two objects arrive at the intersection at the same time, they're going to collide. So for example, if you go to a busy airport, you look up at any given time, there are lots and lots of airplanes. And somebody on the ground is controlling the path of these airplanes. They're going to be flying over the same point, hopefully not at the same time. Yeah? So now we're dealing with the intersection of two curves. That's not too hard to do. The collision of two objects moving with time, that's a more complicated problem. Okay, so remember, collision means two objects or more, here we're dealing with two, arrive at the same point at the same time. Intersection is when the paths of these two things share a common point, but these two objects are not at that point at the same time. Right? So how do we find this kind of thing? Pretty much the same idea as the last example, but now it's a little bit more restrictive because that surface now is another curve. Two curves can intersect at one point at a time. In the last example, finding the intersection wasn't too hard. The time really wasn't that big a deal. Now it's a much bigger deal. So let's check out this example here. We have an object traveling on R1 is equal to t squared, t cubed. And another object is traveling on this second space curve. This one will make it a line. 1 plus 4t, 1 plus 16t, and 1 plus 52t. Well, the two objects collide. Well, their paths intersect. Collision, of course, implies intersection. If you find out they actually collide, then the second question is automatically answered. You have to intersect to collide. But just because the two paths intersect, it doesn't mean they collide. Right? If you and your roommate both have a class in this building, but your roommate comes here at, 10:30, then your paths will intersect, but you two do not collide. You're here at different times. Same location, but different times. Time is very important when we answer the collision problem. If you want the collision to happen, say this is an airplane and you don't want it there and you want to make it come down with something else, then you want them to collide. But normally like in the earlier example with the air traffic controller problem, we don't want them to collide. So let's solve the collision problem first. Remember, collision means same place. That means x, y, and z at the same time. So we're going to take the x component of this first space curve, make it equal to x of the second one, take the y of the first, make it equal to y of the second, and same thing with z, and solve for t. First equation is t is equal to 1 plus 4t, same x, same y, and then same z. And all three equations must have the same t as the solution for the collision to happen. And we can solve these three equations in a variety of different ways. Here's one way to do it, perhaps one of the easier ways to solve this. I can take the first equation here and substitute that into the second one. So I get 1 plus 4t squared, that's t squared, I'm taking this t, into equal to 1 plus 16t. And the solution of this equation right here will satisfy the first two equations. That means whatever t I find out, that means that at that t, x and y will have the same value. Then we just take that t and see if it works in the third equation. That's going to tell us if the third component will intersect. Okay, so one thing at a time. Let's solve this equation first. One plus 4t, the quantity squared, is 1 plus 8t plus 16t squared. And the right-hand side is 1 plus 16t. And this is a quadratic equation. We expect two solutions to come out of this. The ones go away. I can subtract 16t over here, and this becomes negative 8t. 16t squared minus 8t is equal to 0. And that's very easy to solve. Factor 8t out of that. And we see that t is equal to 0 and t is equal to 1/2. Okay, so at these two times, the x and y locations will be the same. But z, the height, can be different. So you can have two things that look like this, but they don't intersect. They have the same x and y, but different z value. It's like you and your roommate have the same class in this building, but your roommate is upstairs. Right? There's no collision. At these t, x and y are the same. Now, to guarantee collision, z also has to be the same. So what we do is we test each of these two values in the third equation. And the third equation is t cubed equal to 1 plus 52t. If this equation is satisfied by at least one of these, then we know there's a collision. If not, then it doesn't happen. Yes? Right. Say that again? Right. But that's just x alone. That doesn't tell us much about whether the two things. We're talking about one component of the location. That's just one x component. T is equal to, oh, I see what you mean here. This equation here. Right. So what happens here is that we took one equation, square that equation. Every time you do that, you may introduce an extraneous solution. So this is a quadratic equation out of the first two equations. The first equation is a linear equation. So we operated on the linear equation, turned that into a quadratic. In doing so, we introduce one extraneous solution that may not satisfy the initial equation. Okay, so what that means is that, what does that mean? Okay, let's hold on to that point. Let's finish this thought right here, because this can actually answer the first question we want to know. Now, if we take either of these into the third equation, does either of these two satisfy the third equation? No, right? So, neither satisfy the third equation. So we cannot find a t that simultaneously satisfies all three equations. As far as the collision problem is concerned, this tells us that collision will not happen. I'll come back to that earlier point. Let me come back to the earlier point. I'll add it to my notes, just like last time with the earlier question, before I upload that. Let's finish the thought here. Collision does not happen. Okay, so they don't collide, but they can still intersect, right? Remember, this is if at the same location, but different time. I will address that question before I upload the notes, so I'm not brushing that aside. I'm not forgetting that. And here are the space curves again. One plus 4t, 1 plus 16t, and 1 plus 52t. To find the intersection here, now we're going to allow these two t's to be different values. And it's helpful if you use a different variable for one of them. And we're running out of time here. I'll finish this up, and you'll see the complete notes here before I upload it. So you do the same thing here. Make the x and y, z equal, and you find s and t. And those will tell you that at these two times, they will arrive at the same location, but they will be a little bit off from each other. Okay, so I will have the questions answered before I upload the notes, and see you next time.
So basically that thing you did right there. Yeah. So when wherever the three equations we are, you got the three equations here, right? Right. So we're going to be logical, okay, to solve for a value of t here. Okay. So you get one value of t since it's linear. Okay. Here you get two values of t. Right. So here you get two values of t. Right. And then you check if at x does it intersect. So you get a value. For example, you get something here. You get -1. Yeah. Okay. Similarly, here you get two values. And if you get t's, all three same t's, then that means that it intersects at that time at that point, right? And it doesn't intersect at the other times you get because you get extra other extra solutions.
That would work if the equations are simple. Sometimes you may have, like, maybe, say, two lines or something. There are times that the equations may not be. But that's actually
in this
example, that would be a very
it makes sense. Right?